Third lecture in our covalent bonding unit. We're going to talk about now is called valence shell electron pair repulsion theory, or it's commonly referred to as Vesper. And the quote that we have here says, in Italy, on the breakup of the Roman Empire, society might be said to be resolved into its original elements, into hostile atoms whose only movement was that of mutual repulsion. Now, it's an interesting quote because that's going to guide our whole Vesper idea, the whole idea of the Vesper theory. Now, number one, you should be able to differentiate between electronic and molecular geometry, and you ought to be able to use the shape of a molecule on a lone pair for electrons and lone pairs to predict the shape. And you should be able to understand the effect of the molecule shape on the stability and reactivity of a particular molecule. So what we already know that atoms can bond together to form compounds. Now we talked about ionic compounds in Unit 5, but in this one we've been talking specifically about covalent compounds, where bonds are or where electrons are shared in what we call bonds. Now atoms can vary in the number of bonds they can form, and we know that we have Coulombs Law and effective nuclear charge. Okay, that's something that we talked about earlier this year. But now with those things in mind, what we learned in the lab. We learned that electron bonds repel each other in the same way that electrons do. Now remember, whenever you have a bond, remember that bond actually represents a pair of electrons. So if you have a pair of electrons here, and you put a pair of electrons there, those electrons are both negatively charged. So because those electrons are negatively charged, they want to repel one another. So these electrons will actually move to the other side of the molecule to be as far away as possible. Now this will actually determine the shape of the molecule by the repulsion of the bonded electrons. Remember, those electrons want to spread as far apart as they can. So now that's Coulombs law. Coulombs law says that like charges repel. We've learned about that earlier this year, and it's going to keep coming up and up and up. Like charges repel, and opposite charges will attract. So electrons, which are bonds, are in bonds, want to get as far away from each other as they possibly can, and that determines the shape of the molecule. So we have what's called the molecular geometry. The molecular geometry is the geometry of the connected atoms to a central atom. Now you have to have what's called a central atom. The central atom is what everything is connected to. Now, you can have more than one central atom in a molecule. So, for example, if you had C, C, and all these are connected to H's, and let's say this one is connected to an O and then an H. These two right here both represent central atoms. Okay, you can't say there is one central atom for the entire molecule. Instead, you say that there are two central atoms. So the central atom represents the middle atom in which everything is connected to. So whenever you're talking about the molecular geometry, you're talking about the molecular geometry relative to a central atom. Now the molecular geometry is determined solely by the bonded elements. So if I were to look at the molecular geometry here for water, we know this is water, I would look solely at the H, the O, and the H. I would not look at the lone pairs at all. That's what we call molecular geometry. Molecular geometry is determined only by the connection of the atoms that are there. Whenever you have a double and triple bond, so if I were to say this is a double bond, that still refers to what we call one electron domain. And we'll talk a little bit more about that later. Electronic geometry, on the other hand, looks at all of the pairs of electrons. So if you were to look at the central atom here, which is once again the oxygen, if you were to look at the central atom here, it has 1, 2, 3, 4 pairs of electrons that surround them. So the electronic geometry of this would be different from the molecular geometry. This one says there's only 2 things connected to the oxygen. This one says that there are 4. So because of that, you can actually use the idea of electronic geometry and molecular geometry to predict the shape of the molecule. So, electronic geometry can be the same as molecular geometry. They don't have to be different. In fact, when you look at this molecule right here, this is methane. If you were to look at methane, which is also known as CH4, it has pair of electrons, pair of electrons, pair of electrons, pair of electrons. Each pair of electrons represents a bond to an atom. So if I were to say this, the electronic geometry, I would say that there are 4 pairs of electrons connected. So there are 4 as far as the electronic geometry is concerned. But there are also 4 atoms connected to it. 1, 2, 3, 4 hydrogens. So there are 4 atoms connected to it. So they can be the same. In fact, the only way that they're different is if there are lone pairs on the central atom. So if you have nitrogen and it has 1, 2, 3 bonds, and then all of a sudden it has a lone pair, that's where you're going to say the electronic geometry differs from the molecular geometry. So, does the molecule below have the same electronic geometry as molecular geometry? And the answer is no, because they have lone pairs. Next, it says, explain why unbonded electrons have a greater effect on bond angles, or a greater bond between angles than bonded electrons. So why is the angle here, that angle right there, we're going to call it 1, and we're going to call this 2. Why is angle 2 bigger than angle 1? And it has to do with the whole idea of the electrons. Remember, the electrons are shared in these bonds. So when we draw it out, we would say nitrogen, and we would have hydrogen, and we would have the electrons somewhere in between. Well, the electrons in the lone pair are right next to the nitrogen. So remember, this whole idea of electrons repulsing each other, because these electrons are further away, you create a greater distance between these bonded, the bonded electrons, than you do with the unbonded electrons. So these unbonded electrons will actually push these other bonds further away than they would if they were all bonded together, because they're physically closer to the central atom. So now we come to Vesper. Vesper stands for valence shell electron pair repulsion theory, and it predicts the molecular geometry based on valence electrons, be they bonded or be they a lone pair. So it's based on the idea from Coulombs Law that electrons will repel each other as far away as possible, and the fact that lone pairs push away more than any other. So there are limitations to Vesper. The first one is that it's limited to covalent compounds. And the second one is that the shapes are not always the same depending on the bond length. So if you were to have a carbon connected to 4 fluorines, it's going to take a particular shape. If you were to take that carbon and then bond it to fluorine, iodine, chlorine, and bromine, you're not going to get the exact same shape. It's going to be pretty close, but it's not going to be the exact same shape. And the reason is these molecules are all of different size. This one is very, very, very small. This one is very, very, very large. And so because of that, there's going to be a little bit of change in the bond angle just to the size of what we call the substituent atoms. And the substituent atoms are the things that are connected to the central atom. We call those substituent atoms. Okay, also Vesper doesn't work very well for transition metals, and that makes sense because transition metals tend to the most part form ionic compounds, but there are some limitations to Vesper. The shapes that are involved, the first one is linear. The first shape is linear because it's anytime you have 2 bonds present, they will repel each other as far as they can. This is as far as these 2 electron pairs can get away from one another. If this one were to move over closer, they'd be closer than they can be, and these would move in the opposite directions. So anytime you have things where there's 2 bonds to it, they will repel each other, and we call this a linear bond. Okay, now you see linear bonds not only when you have 2 bonds present, but also when you have 1. If you have a nitrogen molecule, nitrogen bonded to nitrogen, they're sharing a pair of electrons. In fact, they're sharing 3 pairs of electrons. But when they're sharing these electrons, they can't get any further apart than they are when they're in the bond between them. Next is bent. If you have 2 bonds, but you have a lone pair present on the central atom, remember this lone pair can actually push these molecules down and away from each other. An example of that is when you see sulfur dioxide or water, which is dihydrogen monoxide, or anything that generally involves nitrogen is going to have a lone pair there. Now the difference with nitrogen is it usually has more than 2 bonds, but if you have something that looks like this, okay, you would have an example in which you would have a bent molecule as well. Now because of the proximity of these lone pairs to the central atom, the bond angles can actually vary between 104.9 and 109.5 degrees. But what happens is when you have lone pairs on the central atom, it'll actually squeeze those bonds and it'll actually make it bent. Next we have trigonal planar. Trigonal planar is what you have when you have 3 bonds present, no lone pairs but just 3 bonds. And you see an example is BCl3. And it's called trigonal planar because it's a triangle in one plane. Now, most of the shapes that we go to from now on are going to be in three-dimensional space. So the fact that this one is a triangle in a plane is going to make is why we call it trigonal planar. Now, the bond angles here are 120 degrees because when you go in a circle, you have 360 degrees all the way around, and you want to equally divide this up between the bonds because that's as far away as they can get from one another. Next, we have trigonal pyramidal. Trigonal pyramidal is if you have these three things connected just like we did before, but now you have a lone pair. When you have that lone pair, like we had with nitrogen, 1, 2, 3, okay, that lone pair will actually push these things down and further away, creating different bond angles. Generally, it's about 107 degrees. It can vary once again with the size, but this is called trigonal pyramidal because now you have a triangle and then it actually forms a pyramid with the lone pair. Next, we have tetrahedral. Tetrahedral is what you have when you have 4 bonds present. The example we have with that is methane. And whenever you have methane present, these things actually move into 3 dimensions at this point. So you have one go up, you have these things kind of go in the traditional trigonal pyramidal, and then you have this one that goes up right here. These bond angles are 109.5 degrees, and that's as far as these 4 things can get away from one another in 3-dimensional space. Next is trigonal bipyramidal, and that's when you have 5 things that are present. And so it takes this kind of shape right here. It's called trigonal bipyramidal because once again you see the trigonal planar structure, but then you have one pyramid as it goes up, and then you have another pyramid as it goes down. And so you see you have 2 different pyramids, and so that's why it's called trigonal bipyramidal. This is what happens when you have 5 bonds connected to something, and once you have 5 bonds connected to something, it's generally considered to be an exception to the octet rule. And it only happens if you have something that's in the 3rd period or further. So if it's in the 4th period or the 5th period, those are the only things that can be exceptions to the octet rule. So you won't see oxygen or nitrogen or anything like that be an exception to the octet rule, but you will see phosphorus. An example of this is phosphorus pentachloride. So phosphorus pentachloride will assume a trigonal bipyramidal shape. Next, you have an octahedral, and this is the last shape we're going to learn. It says that there are 6 bonds that are present, and they'll oppose each other. So once again, we have this one up, one down, but now we've added another one, so we need to get a square plane. So you see a square right here, and then you see it go up right here. And you see the pyramid that goes down. And when you draw it like this, this is the shape of an octahedron. You have one side, and then it's hard to draw in 3 dimensions, but 2, 3, and there ends up being 8 sides. That's why it's octahedral. Now, one thing you need to be concerned with here is octahedral. A lot of people say, oh, 8 bonds because of octa, and it's no, that's how many sides there are whenever you connect everything. But an octahedral has 6 bonds. Now, the bond angles are a little bit different. They're going to be 90 degrees in the plane because you've got the square. They're going to be 180 degrees between the top and the bottom, and then they're going to be 120 between some of the whenever you look at 3 angles like this, one up, one down, and then over here. So you have different bond angles that are different because of the shape, but octahedral is the last one that we're going to learn. So just like we had with trigonal bipyramidal, this is going to be an exception to the octet rule again, so it needs to be the 3rd period or greater. Now there are lots of other shapes that we're not going to look at, but you can have an octahedral shape that then has 2 lone pairs. There's a whole bunch of shapes if you're interested in looking at them, but this is where we're going to kind of draw the line. So it says use the clear method to explain why the geometry of water as bent and not tetrahedral. And the reason why is we're referring to the molecular geometry. If you were referring to the electronic geometry of water, you would have these lone pairs right here, and you'd actually be right to call it tetrahedral as far as the electronic geometry is concerned. We're not interested in the electronic geometry. Instead, we're looking at the molecular geometry, which is only the 2 things that are connected to it. So even though these electrons are here and they're repelling it and they're the reason why it takes this shape, when we're looking at molecular geometry, we are only referring to the atoms that are present. Next it says predict the polarity and molecular geometry of this. And there's actually an interesting thing here. You can actually draw this molecule 2 ways. So the first thing is you can draw it here, connected to an H, and a Cl2. So if you were to look at this, you can look at this central atom, and you can look at this central atom, and both of them are trigonal planar. And it doesn't matter how you draw this molecule, but it ends up being trigonal planar for both carbons. But the way that I drew it here would definitely have a polarity. This chlorine is pulling down, this chlorine is pulling down, so there's going to be a net pull of electrons down. If I were to draw this molecule a different way, say like this, the pull of the electrons by the chlorine would be canceled out by the pull of the electrons of the chlorine. And so this one would be considered to be nonpolar, this one would be considered polar, depending on how you draw it. It says an element has to be part of what chemical family in order to be the central atom of an octahedral molecule. So remember, to form an octahedral molecule, it needs to form 6 bonds. Well, the only thing that can form 6 bonds is going to be something that has 6 electrons in it, because it can contribute 1 electron to each bond. So the things that have 6 valence electrons in them are going to be sulfur, not oxygen, because oxygen can't be an exception to the octet rule, but sulfur is it, and so you're going to have group 16, or sometimes it's referred to as the chalcogens. Now, the shape and the reactivity. The shape of the molecule will determine how molecules react, in fact, how reactive they are. A lot of times, the interaction of molecules says, okay, I've got a molecule right here that if it can hit this part of this bond, it will actually form a way in which this thing can connect to these molecules. But if the orientation is different, it can't get there. Well, now think about that in terms of a molecule. If you have sulfur that's surrounded by 6 molecules, it's going to be very difficult for an atom to come over here, let's say this is a hydrogen, to come in and get to that sulfur, because it's got all these fluorines blocking it in the way. So the more things that are connected to it, the more difficult it is to access this central atom. Also, depending on what's connected here, this will pull the electrons out, making this thing more positive or more negative. Generally, it's more positive. So therefore, it's more likely to attract something like a chlorine to come closer to it. So now, the reactivity and the general shape of a molecule is very much influenced by the shape of the molecule and by Coulombs Law. Now, Coulombs Law is kind of the underlying thing on most of the periodic trends and the shape of a molecule.